Hello everybody, this video is going to be a continuation for chapter 8 and we are going to be covering on chapter 8.3 on radian measure as well as chapter 8.4 on arc length and area of sector using radian measure. The objectives of today's lesson is to convert angular measure from radians to degrees and vice versa. And we will be using the formula s equals to r theta and a equals to half r squared theta to solve problems involving arc length, area of sector, and area of a segment of a circle. Before we begin, let us first recall some concepts that we have covered in the previous lessons. In the previous lessons, we have already understood what is the meaning of a chord, an arc, sector, as well as segment. And in the most recent lesson, we have learned the formulas for length of arc as well as area of sector. We have also covered how to find the area of a major segment, for instance PSQ, which is this part over here. And that can be found by considering the area of the major sector plus the area of a triangle. Next, if I were to find the area of a minor segment, which is this area here, we will consider the area of the minor sector OPRQ minus away the area of triangle POQ. In a separate video found in the SLS lesson, you would have learned how the radian measure came about. Regarding the radian measure, we will need to know how to convert between radian measure to degrees, and that is relying on the fact that pi radians is equals to 180 degrees. And due to this fact and knowing that pi is a number, we can say that 1 radian is actually 180 over pi degrees. Or we can also say that 1 degrees is actually pi over 180 radians. How we understand this is just like how in primary school, we understand as though pi units, thinking that pi is just a number, it will be 180 degrees. And if you are going to find out what is the value of 1 unit, we will usually take 180 divided by pi. Okay, so therefore we are able to tell that 1 radian is equals to 180 over pi degrees. We can do the same on the other opposite side, okay, in order to achieve this. Let us do some practice in trying to convert the following angles from radians to degrees. So in part A, we are given pi over 15, and whenever the question has pi inside it, we need to recognize that it is usually referring to radians measurement for the angle itself. So in order to convert this radians into degrees, we will take pi over 15 times 180 degrees over pi, because we know that 1 radian is 180 over pi degrees. So we see that we will get 12 degrees. We can do the same for part B as well, where we multiply by the same value. For part C and D, we have 3.04 and 8. Do realize that 3.04 and 8 are also considered as radian values, okay? Because after all, if we understand as pi to be a number such as 3.1412 and so on, when we divide by 15, we eventually do get a decimal value somehow. So in part C and D, they are also radian values. So we also do the same, and we get when we round it to 1 decimal place because the answer is in degrees, and we will get these answers. I would also like to add on that do not assume that just because we have 3.04 and 8, whereby the numbers look rather small, then we jumped into the conclusion that they will be radian values. I know that it is radian value because the question actually specified that it is radian in the first place. Okay, usually radian values tend to be on the smaller side, okay, but we shall not rely on that assumption, because there could be angles in degrees that are also small as well, and that is possible. And now, taking a look at Practice Now 7, we want to convert each of the angles shown from degrees to actually radians. So we see that whenever they are in degrees, we will put in the degree sign. This is in contrast to when it is in radians, as per what we saw in Practice Now 6. So when values are in radians, we usually do not write in RAD, because the word RAD is actually not a unit itself. Okay, it's not a symbol for units. So going back to Practice Now 7, what we will do is to consider this conversion here, where we multiply by pi over 180 degrees for each of the values, and we will get our answers to be as such. Do take note that when answers are in radians, we round off our answers to 3 significant figures. So this is the part where I would like to address what I have always been saying about angles in degrees and needs to be in 1 decimal place. So at this juncture, we have started to explore that angles can be expressed as radian unit, or otherwise it will be in degree units. For a very long time, we have been looking at degree itself. So when it is in degrees, we will always round off our answer to 1 decimal place as per exam requirement. Whereas if it were to be in radians, our answers should actually be rounded off to 3 significant figures. In the previous Practice Now examples, you would have seen that when I do conversion from radians to degrees or degrees to radians, I did it in a very traditional working manner where I do not rely on calculator. We shall continue to use it in that manner and not rely on the calculator to do the conversion, although some of you may actually acquire the skill from other YouTube videos or maybe from your other tutors. So we will only stick to conversion by making use of what we understand about pi radians being equals to 180 degrees. So coming back to this, I will want to address on how to use the calculator when angles are in radians. So always ensure that you're in the correct mode when using your calculator for calculations involving angles. This is extremely important. Okay, because when angles are in radians, you got to be set in radian mode, and if your angles are in degrees, your calculator has to be set in degree mode. Otherwise, when doing calculations when involving trigonometric functions especially, okay, such as sine, cosine or tangent, the value that you will get will not be the same. Okay, so I will be attaching 2 separate videos in learning how to convert your calculator into the respective modes. You need to know how to do this on your own during exams as well. So if I were to consider, for example, sine 45 degrees and pressing that into the calculator in degree mode, okay, I will be able to get the value about, let me write this clearly, 0.70710 and so on. However, if I put sine 45 in radian mode, okay, so this one, I put this in degree mode, okay, and this, if I were to put in radian mode, okay, I will realize that the answer is going to be 0.85090. So I hope that you see that discrepancy over there. Do give it a try, and I hope that you realize the difference. And it is going to be very dangerous if you don't change to the correct mode, because if you don't change it, then during the exam itself, you may end up losing most of the marks in the paper. In a separate video from the SLS lesson, you would have learned how the arc length and area of sector formula came about when we are using radian measure. So the 2 formulas that we need to know is that the length of arc is r theta and the area of sector is half r square theta. But in this case, the thetas are actually angles in radians only. We cannot apply this formula when we are doing angles in degrees. So let us now take a look at Practice Now 12 to practice our formulas that we have just learned regarding arc length and as well as area for sector when we are using in radian measure. So in this question, we are given that O is the center of a circle of radius 6 cm and the reflex angle AOB is 7 pi over 4 radians. Okay, we want to find the length of the minor arc APB, which refers to this side over here. Okay, so if we recall the formula, it is S equals to r theta, where actually S refers to arc length. I usually do not use the letter S. Okay, so usually I will do arc length. Alright, but as long as you are clear, alright, it should be fine. So now taking a look at this question, okay, the radius r is actually 6 cm and the angle theta has to be the angle AOB because we are trying to find the arc length APB. Okay, so the angle AOB, alright, is actually 2 pi minus away 7 pi over 4, okay, which is the reflex angle, and just directly pressing this entire thing into the calculator, we will get the value 4.7123 when truncated to 5SF, and final answer should be left to 3SF, which will then be 4.71. Moving on to Practice Now 13 question 1, we are given a sector as shown with radius 12 cm and the perimeter is 33 meters. So do take note that the question gave us perimeter, and in perimeter would refer to having the two radii as well as the arc length. So we want to find out what is angle AOB in radians. Okay, so the question also wants us to find it in radians. So we need to first find out what is the arc length, and that can be done by taking the perimeter minus away the two radii. So that means that it will be 9 meters. So using the formula S equals to R theta, okay, we will find that theta would actually be the arc length divided by the radius. So you'll find that the formula actually is very convenient as compared to if we were to be doing the angles in degrees. So we just have to simply take 9 divided by 12, and we get that the answer will be 0.75 in radians. And now we take a look at part 2, where we want to find the area of the sector OAB. So we have earlier already found out what is the angle AOB, which is 0.75. Then using the formula for area of sector when the angles are in radian, which will be half r squared theta. Okay, so area is equals to half r squared theta. So the r value is actually the radius 12 and the theta is actually 0.75. So keying this entire thing into the calculator, we will get 54 meters squared. Moving on to Practice Now 13 question 2, we are given that there is a circle of radius 5.5 cm that has a sector with an area of 30.25 cm squared. So this has this area value. We want to calculate the perimeter of this sector. To calculate the perimeter of this sector, we need to know what are the length of the two radii as well as the length of the arc. So we are missing only the length of the arc. So in order for us to find the length of the arc, if I want to apply the formula S equals to R theta, I will need to know what is the angle over here. So we let the angle, subtended angle, be theta. So half times 5.5 squared times theta is equals to 30.25. That is the equation that we can form by making use of the sector area. Then we do some manipulation and we find that the angle is actually 2. Usually we do not write radians, okay, because as mentioned, radian RAD is actually not a representation of the unit itself. Okay, it is not a unit at all. So we need to understand that when there is no unit written for an angle value, okay, it is always referring to radians. So moving on, arc length is actually S equals to R theta. So we have the radius 5.5 and the angle 2, and we get that the arc length is 11 cm. Then piecing everything together, we will get that the perimeter will be 22 cm. We now take a look at Practice Now 14, and in this figure, we have AB that is an arc of a circle, center O, with radius 19 meter. So P is a point on OB such that AP is perpendicular to OB and angle AOB is 0.98 radians. Okay, so we want to show that OP is approximately 10.6 meters. So you must be wondering, okay, what about this one? There is the word radians over there. Sometimes in question, they will actually try to emphasize it. So they will actually put in the word radians to be very clear to the students. Okay, but usually we will not write it. So anyway, going back to the question, part I, we want to show that OP is approximately 10.6 meters. So OP is this distance here, or rather this length here. And it is actually, it can be considered, okay, to be part of this triangle, this right angle triangle over here. Okay, so if I were to refer to this right angle triangle, we actually have the hypotenuse of this right angle triangle, and we know the angle to be 0.98. We can apply our tuakaso, okay, our trigonometric functions, to actually get this equation here, whereby we have OP as the adjacent side and 19 to be the hypotenuse. So by doing some manipulation, we will have 19 times cosine 0.98. I want to caution you over here, when doing this calculation, make sure your calculator is in radian mode. Because if it is not in radian mode, then your value will not turn out to be 10.583. So the question wants us to show that it is approximately 10.6 meters. So therefore, we round it off and we get 10.6 meters. Okay, and that is how we show it. And now in part 2, we want to find the length of AP. So AP also likewise belongs to the right angle triangle, OAP. Okay, so we will also use our trigonometric functions and we apply it such that this 19 meter is the hypotenuse and AP is the opposite side to the angle 0.98 radians. So therefore we apply sine and we have this equation here, and then after doing some manipulation and ensuring that our calculator is in radian mode, we will then be able to get 15.8 meters for the answer in part 2. Next, we take a look at part 3 where we want to find the area of the shaded region. To find the area of the shaded region, we need to consider finding the area of the entire sector, followed by finding the area of the triangle, and then minus we will take the sector minus away the triangle. So first, we find out what is the area of the sector by using half r squared theta, okay, using that formula itself. And then after that, we will get the value 176.89 when truncated to 5SF. Then the area of triangle AOP can be found by taking half times base times height. Okay, so the base will be OP and the height is AP. And these are values that we have found in part I and part 2. Okay, so I will get the value 83.444. So I will then take the sector minus away the triangle, and I will finally get the value 93.4 meters square when rounded to 3 significant figures. Moving on to practice now 16, we are given that this figure shows a major segment ABC representing the cross-section of a tunnel in a children's toy set. So with center O and radius 4.8 cm, such that angle AOC is 2.4 radians. In part I, we want to show that AC is approximately 8.95 cm. So AC is this length here. Okay, I want us to focus on this triangle where we have 4.8 cm for the length OA, and obviously for 4.8 cm will also apply to OC because it is also the radius of the entire circle. So focusing on this triangle, we will be able to find AC by using our cosine rule, such that we will get this equation over here. Okay, and that value will be about 80.059. Then we take the square root and we will find that AC is about 8.95 cm when rounded to 3SF. So this is how we would have shown the answer. Next, in part 2, we want to find the length of the major arc ABC. So we will use the formula S equals to r theta. Okay, and we have the radius 4.8 cm and theta to be 2.4, but the 2.4 radians is actually referring to angle AOC. But since we're trying to find the length of the major arc, we need to know what is the reflex angle AOC. Hence, we take 2 pi minus away 2.4. The reason why I take 2 pi is actually because we mentioned that pi is equals to 180 degrees. So for one full circle, it will be 360 degrees. Okay, so that's why we will have 2 pi minus away 2.4. And we will get the final answer to be 18.6 cm. In part 3, we want to find the area of the cross-section of the tunnel, okay, which is the area of the major segment ABC. So as mentioned right at the start of the lesson, to find out the area of a major segment, I need you to recognize that it is a combination of two items. First of all, it is the combination, first of all, it is the area of the sector OABC. Then after that, we also have to consider the area of this triangle AOC. So what I have in my calculations here is that I have half r squared theta, okay, to find out the area of the major sector. And to find the area of the major sector, I will need to know the area, the angle of the the value of the reflex angle AOC, and that will be 2 pi minus 2.4, because I cannot take 360 degrees minus 2.4. Okay, so if I were to write things like that, this is definitely a no-no, because this is in degrees and this is in radians. Okay, surely we cannot do that. Alright, so then to find out the area of the triangle, we will use half AB sine C. Okay, so A being 4.8 cm over here and B being OC. Alright, and then sine C would be the 2.4 radians. So this is the area of the triangle. Right, and therefore we will be able to get 52.5 cm square rounded to 3 significant figures for this answer. Moving on to exercise 8D question 14, we have this figure that shows a sector of a circle OAB with center O and radius 8 cm. The point P lies on OA such that OP to PA is actually 3 over 2. Okay, so we need to take note of this important ratio over here. And the point Q lies on OB such that OQ is to QB is 3 is to 4 ratio. So given that angle AOB is 0.8 radians, we want to find the length of the arc AB. Okay, so using the formula S equals to R theta, the radius is 8 and then the angle is 0.8, so we will get 6.4 cm for the length of the arc AB. Moving on to part 2, we want to find the area of the shaded region. To find the area of the shaded region, we will consider finding the area of the entire sector first. Then we minus away the area of this triangle OPQ. So how could we go about doing that? Okay, so the area of the sector wouldn't be an issue because we will have half r square theta. Okay, that's in my calculation here. So area of sector. But when it comes to the area of the triangle, I need more information, because if I want to use half AB sine C, I will need to know the length of OP as well as the length of OQ. So earlier on in the question, it says that OP over PA has a ratio of 3 over 2. So that means that this is 3 units and this is 2 units. This tells us that OA would be 5 units in total. Okay, so these are units. So therefore, OP is actually 3 out of 5 units of the entire length 8. So that's why I will have this calculation here. And then the value for OP would be 4.8 cm. We do the similar thing to OQ, where we understand from the question that OQ is to QB has the ratio of 3 is to 4. So translating that into the diagram, it means that OQ occupies 3 units and QB occupies 4 units. That means that OB actually is a total of 7 units. So therefore, OQ is actually 3 out of 7 units of the entire length OB. Hence, we have 3 over 7 times 8. And we find that the length of OQ would be 3 whole and 3 and 3 over 7 cm. So using the formula half AB sine C, whereby C is 0.8 and making sure it is in radian mode, we will get the value to be 19.7 cm square when rounded to 3 significant figures. Now we take a look at exercise 8D question 18, where the figure shows the cross-section of a water pipe of radius 15 cm. Water flowing in the pipe has a height of hcm and horizontal width of 22 cm. So the water actually flows, or rather is in this area here, because water will actually abide by gravity. When we have a round pipe, it should be all the way at the bottom first. Okay, so in part I, we want to find out the value of h. So to find out the value of h, we would consider the entire length. Okay, let me erase the water away. The entire length of the radius, and then minus away the perpendicular height of the triangle OAB. So to find the perpendicular height of triangle OAB, if I were to abstract that triangle out, okay, because it is supposed to be a perpendicular height, it will look something like this. We will have 15, and this entire length is 22 cm. Okay, the question is, can we actually divide it into half just because it is a perpendicular length? The answer is yes, and that is because, okay, the other side of the triangle here, has the length of 15 cm, and this makes the triangle an isosceles triangle. So because it is an isosceles triangle, therefore for this perpendicular height, it will also be a bisector of this base here. So therefore it will be 11 cm on each side of the right angle triangle. So using my Pythagoras theorem for this particular triangle, where I now have 15 and 11, I want to find out what is this height. So Pythagoras theorem will be able to help me to get the value 10.198 cm. So now that we have the height already, the entire radius over here is actually 15 cm, although it may not look like it very much in this diagram because it is hand drawn after all. Okay, so we take 15 cm minus away the height of triangle OAB, and we will then be able to get our final answer to be 4.80 cm. In part 2, we want to find the area of the cross section which contains the water. So the part that contains the water is the part that I've shaded over here. And in order to find out what is the area of this segment, okay, I will need to consider the area of the area of the minor sector here, and then minus away the area of the triangle AOB. But in order to do that, okay, I will need to first and foremost find out what is the angle of AOB. So to find out the angle of AOB, we will refocus to this triangle. Okay, we are aware that this is 15 cm for OA and AB is actually 22 cm. What about OB? So as mentioned previously in part I, we know that it is 15 cm. So now that we have the three sides of the triangle, I will be able to apply cosine rule to find out what is angle AOB, which is what I've done over here. Then doing some manipulation, I will find that cosine angle AOB is negative 17 over 225, and that will mean that angle AOB is about 1.6464 in radians. So once again, when you do even cosine inverse, you got to make sure that your calculator is in radian mode. Now that we have found out what is the angle, it will really facilitate us in finding out the respective areas. So to find the area of the sector AOB using the formula half r square theta, okay, I will be able to get 185.22. Sorry, 0.22. Next, area of triangle AOB will be half AB sine C. Okay, so A and B will be 15 and 15, and then sine C will be 1.6464. Once again, this is a trigonometric function for radian angle. Make sure that you are in a radian mode. So now that we got the areas required, we will piece them together and we will have the cross-sectional area to be 73.1 cm square. I want to take note that 73.0 is also going to be accepted if you use exact values for the areas of sector and triangle AOB. That means you did not calculate beforehand for these truncated 5SF values. Okay, so you actually lump them up together and directly key the entire phrase into the calculator. So when you have that, okay, and after you round off, you will actually get 73.0 instead. So these answers will all be accepted. Let us now take a look at question 24 found in exercise 8D. This figure shows a circle, center O and radius 12 cm, and given the angle POQ is 1.2 radians and PR is a tangent to the circle. So later on in this year for EMATS, you will learn that when a tangent is to a circle, okay, the tangent itself would actually be perpendicular to the radius. Okay, but actually in this question, they did tell you that angle OPR is pi over 2 radians as well. Alright, but later on in the year, this information may not be provided and you need to make that realization. Then subsequently, it says that the length of PR is equal to the length of arc PSQ. This will be an important information later on, okay, in the later part of this question. So in part I, we want to find the length of the arc PSQ. Okay, so the length of the arc PSQ is actually this length here. So since we know the radius and we know the angle, okay, we will be able to apply the formula and we will get 14.4 cm. Moving on to part 2, we want to find the area of the segment PSQ. Okay, segment PSQ, so you need to recognize what is considered a segment do not confuse it with a sector. So that actually refers to this section here. Okay, so in order to find the area of this minor segment, in fact, we will need to consider finding the area of the minor sector OPSQ and then minus away the area of triangle OPQ. So to find the area of the sector, I use the formula half r square theta, and to find the area of the triangle OPQ, I use half AB sine C. Okay, so after getting the values, we will then get the final answer to be 19.3 cm square when rounded to 3 significant figures. In part 3, we want to find the length of the chord PQ. So PQ actually is referring to this line here. Okay, so this line is actually part of this triangle OPQ. So what we can do is that since I know the length of OQ, it will also be the same as the length of OP because they are all radius. Okay, and we got this angle 1.2 radians here. So what we can do is to apply our cosine rule to have the answer 183.64 for PQ square. Then when we take square root, we will get the value to be 13.6 cm when rounded to be 3 significant figures. Finally, we will take a look at part 4 where we want to find the area of the shaded region PSQR. So in order to do that, we need to first know what is the area of the triangle PQR. Okay, so when we know the area of the triangle PQR, we will then minus away the area of this segment which we have already found in the previous part. That would then allow us to know what is the required answer for area of shaded region. So as mentioned earlier in the question, there was an important information that says PR is actually of equal length to the arc PSQ. Okay, and earlier on we found that the length PSQ is actually 14.4 cm, and that is going to be very helpful. Okay, next, for angle OPR, in the question itself, it also said that it is pi over 2, it is 90 degrees. Okay, so at this point, I hope that you are familiar with certain angles that are going to be very important. Okay, so pi is 180 degrees, pi over 2 will be 90 degrees, and 2 pi will be equals to 360 degrees. So these are some commonly used pi radian values. Okay, so angle OPR, alright, given in the question was 90 degrees, which is actually pi over 2 radians. So for angle OPQ, okay, that will actually be pi minus away 1.2 divided by 2. So how did I actually get that? Okay, I got that because in the triangle OPQ, we know that this is 1.2 radians, and OP is actually a radius, OQ is also a radius. So it makes the triangle OPQ an isosceles triangle. So because it is an isosceles triangle, an angle sum of triangle will be 180 degrees. So I will take pi minus away 1.2 radians, and I will know the sum of the base angles. Okay, and I divide by 2 because the base angles are going to be equal. So this is where I applied base angles of isosceles triangles. So after I find out what is angle OPQ already, I will then be able to find out, okay, let me erase some parts here. Oops, okay, this is the objective. Alright, so just now we mentioned that this is 90 degrees, okay, which is pi over 2. Okay, and then now we understand that this value for OPQ is about 0.97079. So that means that for angle QPR, okay, this section here, it will be 90 degrees minus away that. But of course, we're not talking about degrees here. We are doing radians. So I will do pi over 2 minus away the angle OPQ, and I will get this value. Do notice that I took more than truncated 5SF. I took more, one more digit because I saw that there's a series of zeros. So to give high accuracy, I took one more value, one more digit that is not 0. So now let us piece up all this information. Okay, So earlier on, I said that we need to find the area of the triangle PQR, and I do that by doing half AB sine C. Okay, 13.551 and 14.4 are the lengths PQ and PR. Okay, so because question says PR is the same as the arc length PSQ, and PQ is the length that we have found earlier on in this question. Then we minus away the area of the segment. So perhaps let me just write down instruction here first. So this is the area of triangle PQR, and over here is the area of segment PSQ to be exact. Okay, then keying that into the calculator, and we will get 35.8 cm square when rounded to 3 significant figures. We have now come to the end of today's lesson, so please complete the homework in exercise 8D, questions 5, 12, 17, 23, and 25. The homework will be due on Wednesday, 24th of June. I'll see you again. Bye bye everyone.